All right, ND engineering videos. So, here's a problem. It's a dynamics problem dealing with pulleys, motion and acceleration. So here we've got a problem where we've got a motor and it's hooked up to this series of pulleys. And the motor has a velocity A that's pulling the cable in. And we have this block down here B that has a velocity going up. And it's our job to determine the time needed for the load at B to attain a speed of 8 meters per second starting from rest. If the cable is drawn into the motor with an acceleration of 0.2 meters per second squared. Okay, so we're going to say that this is 0.2 meters per second squared. So right off the bat, the first thing we can do is start to establish some datum lines. Whenever you get a pulley problem like this, you can go ahead and analyze it by saying, where are the cable lengths going to be fixed? And what I mean by that is we can put, for example, a datum line right here, because we know that this cable length in between this left red dotted line and this right red dotted line are going to be the same. And we can measure this point A to be a fixed point somewhere that will move back and forth with the movement of the cable. So that's our one datum line. Another datum line that we can set up is right here and right here. And the reason that we can do this is that we can say these four cables in here, their length are going to move at the same rate. And that should become more apparent here pretty quick. So let's go ahead and label these. We'll call this SB, and we can call this one up here SA. So these cables out here outside of the datum lines, we're going to ignore them because their lengths aren't really going to change. They'll be there and there will be cord moving through them, but the distance from here to here is always going to remain fixed. However, the distance between here and here can move, and this point A is also going to move. So, that being said, let's go ahead and write an equation for describing the length of the cable. As you can see here, we have 1, 2, 3, 4 cables within the SB range. So we can write that as 4 SB plus, because we have an extra cable, plus 1 SA. And we can just set that equal to 0. Whenever you have a pulley problem like this and you're trying to describe the length of the cables, you can always just set them to 0. Because what that'll do is that'll allow you to say it's some fixed length that you know these plus those is going to equal the total length of the cable. This over here is unitless for the time being. Okay, we're also asked to describe, let's see here, speed, and we also have acceleration. So let's go ahead and describe these in terms of speed, velocity, and acceleration. Well, it just so happens to be that the velocity at SB is going to be the same thing. It's going to be 4 VB B plus, well, actually, no, it's not going to be plus, because as B is increasing, A is going to decrease. So we're going to have to move A to the other side. So we're going to say negative VA. Okay, now let's try and write this in terms of acceleration. We can again say that we have 4 VB, and we're going to say that that's equal to the negative acceleration at A, because we're going to move this, subtract that from the other side. Now, if this doesn't make sense to you, let me explain it just a little bit better here. Basically, when the motor's going in, these cables are shortening. So A is moving at a different acceleration compared to these cables. Because with a pulley system, every time you add a pulley in, your speed decreases by half. So that's kind of where we're going at this. I encourage you to pause the video and think about it. All right, so let's move on here. So we're asked to determine the time needed for the load at B to obtain a speed of 8 meters per second. All right, well, sounds simple enough. So if B is moving at 8 meters per second, well, we can just say that, or sorry, let's do acceleration first. So let's go ahead and find acceleration. We're going to say that negative, because we can rearrange this equation over here, negative 0.02, and that's coming from here, and that probably confused you, negative 0.2, right, is equal to, and we'll say that this, just to make it easier for everybody, we're going to say is equal to 4b. We'll say 4ab, so 4, and that should be an a actually. Sorry about that, guys. AB is going to be equal to 4ab, the acceleration at b. And we can solve this then to find that the acceleration at AB is equal to 0.05 meters per second squared. Okay, so we found that the acceleration at B is going up at 0.05 meters per second. And all we need to do now is determine how long it's going to take this B, since it's starting at rest at 0 meters per second, how long is it going to take it to get to 8 meters per second? Well, there's an equation that you can use, and that equation is going to be equal to V is equal to V naught, the starting velocity, plus the acceleration times the time. Okay, so this V right here is going to be our final velocity, okay? Final velocity. That's what we're going to solve for. V naught's initial, we have acceleration, and we have time. So let's go ahead and plug in for these. We know that our V is supposed to be equal to 8 meters per second. And we'll draw that in yellow, so that way you guys have a little bit better idea what's going on. So 8 meters per second, and that's coming from right there. And we know that that's going to be equal to the initial speed, which is 0 meters per second, right? And we have an addition of an acceleration times time. Now we don't know time, that's what we're trying to solve for. But we do know the acceleration, which we solved right there. So we can say that that is going to be equal to 0.05 times the time, okay? Times the time. And solving for that, we find out that we get the time is equal to 160 seconds. 160 seconds for block B to reach a speed of 8 meters per second. And that there is how you do a pulley problem.